Right now, if this thing is also accelerating rotationally, but not only have tangential, time is going to have tangential acceleration. Not only will it have centripetal acceleration, it's also going to have a tangential acceleration. What that means is this is moving in this direction. It's actually speeding up. So which means that the speed is increasing or decreasing in this direction. Okay, now it's got two different accelerations, just like it's got inside the centrifuge. Initially, we were just bringing them up to 12 G's, right? So because of the tangential motion, it's got its centripetal acceleration, but also it's rotational. There's a rotational acceleration. This thing is speeding up. So because of the rotational acceleration, it's also got a tangential acceleration. Notice that you've got two vectors. So the total acceleration is going to be this vector that you're looking at, right? And there's going to be an angle involved, right? So if this has both tangential and centripetal accelerations, then the total acceleration is going to be the vector summation of these two. So what you're looking at is, in essence, you turn it into a small triangle. So this is the centripetal acceleration, this one is. Right, so this becomes a base of a triangle. This has the same length as this one is. So this is the tangential acceleration is going in the opposite direction. And notice that hypotenuse becomes the total acceleration. That's the net acceleration of the system. So square of this plus the square of that is going to give you a total acceleration. The total acceleration is also going to have a direction. Right? So the net acceleration and total acceleration do not necessarily point towards the center of a circle. All right. So it can be pointing at a different angle that you're looking at. So this time, obviously, tangent is opposite of the adjacent. It's going to give you the tangent. So you can find the angle, and you can also figure out the total acceleration of the system. So A represents the total acceleration or the net acceleration. Centripetal acceleration is speed of square of the speed divided by r, or you got r times the rotational velocity squared. So that's your centripetal acceleration. Tangential acceleration, if you know the angular acceleration multiplied by r, it's going to give you the tangential acceleration. So the acceleration is going to be meters per second squared. All right, so you got the centripetal acceleration, you also have the tangential acceleration. So the net acceleration is going to be a vector, not necessarily pointing towards the center. Okay, so now let's take a look at a simple problem to illustrate this one. Okay, so we got a merry-go-round. It makes a revolution. It takes 4 seconds for a single revolution. So it's just going to go around. One single revolution is going to be 4 seconds. So we are trying to figure out the linear speed of a child seated 1.2 meters from the center. And what's her acceleration? Okay, I'm just going to do part A as a demonstration. All right, so one single revolution expressed in terms of angular displacement take 4 seconds. So one single revolution will take 4 seconds. So what's the linear speed? That's the tangential speed. That distance of 1.2 meters away from the point of rotation. It's almost 1.2 yards, almost a yard, 3.5 feet, give and take. And what's the acceleration? I'm just going to do part A. All right, so tangential velocity is what we're looking for. Here's the formula for the tangential velocity. All right, so if you know the angular velocity, you can get the tangential velocity. Angular velocity is how fast angular displacement changes in time. So how fast the angular displacement changes in time. So changing angular displacement is the same as theta. And that's it. That's the final formula. And then plug the numbers in. All right, so R is going to be 1.2. Theta is going to be a single revolution. Single revolution is going to be 2 pi. Instead of using pi, notice that I'm using 3.14. Okay, so every time you see pi, use this number. Right? T is the time, which is 4 seconds, so it's going to give us a tangential velocity. In terms of miles per hour, it's going to be 4 miles per hour. All right, so constant angular acceleration. Okay, so what if this thing is speeding up or slowing down at a constant rate, rotationally? Okay, so we'll take what we know from uniform motion, constant acceleration, and then we'll just transform everything to rotational motion. So x displacement is going to become angular displacement. Initial velocity becomes angular velocity. Final velocity becomes final angular velocity. Acceleration becomes angular acceleration. So what we do is we will just transform these equations to new equations. So these are going to be our transformations. Right, so the first formula, this becomes theta, this becomes omega naught, this becomes alpha. So we'll just modify the first formula. Right, so x becomes theta, b becomes omega, and e becomes alpha. Okay, that's it. Second formula, V becomes omega, V naught becomes omega naught, A is going to become alpha, and then T is still T. Right, so this is omega, this V squared becomes omega squared, VO squared becomes omega naught squared, plus 2 times alpha times theta. Okay, that's it. So these are the transformations. Okay, so when do you use these equations? End up using these equations when the acceleration is constant. So this is going to give you predictable motion. So these equations will got the linear equations. Now we are using the. All right, problem number 5 would be a good example of this one. Okay, so what do we have in problem number 5? All right, so we got a car engine slowing down. It's going from 4,500 RPMs, revolutions per minute, to 1,200 revolutions per minute within 2.5 seconds. Okay, so figure out its angular acceleration, assume constant, and also figure out the total number of revolutions the engine makes in this time. So while it's slowing down from 45 RPMs to 1,200 RPMs, number of revolutions within that time period. All right, so once again, list everything. So we got 4,500 revolutions per minute, so that's the initial speed. So it's going to go from 4,500 revolutions per minute to 1,200 revolutions per minute within 2.5 seconds. What's the angular acceleration? And how many revolutions it's going to make within that time period. Okay, so revolutions per minute, literally the most difficult thing in this chapter is probably going to be these weird conversions. Revolutions per minute needs to be expressed in terms of radians per second. So you have to get to the proper unit. So you got 2 pi radians. Okay, so 1 revolution is going to be 2 pi radians. And then 1 minute is going to be 60 seconds. All right, so you have to do the conversions to radians per second. Okay, that's the only thing you have to be careful of. Everything else is you guys are good at it. Okay, next question is, based upon all the symbols that we have, the best formula to pick is this one, obviously. And then isolate alpha. And done. This was easy. All right, so end up putting the numbers in terms of revolutions, in terms of radians per second. And we end up getting a number, and that's it. Okay. There's no converting this number to anything
3, 2,
more significant than that is.
1, mark.
Here at the Vita Corporation Flight Simulation Lab in Warminster, Pennsylvania.
Hold on. Okay.
3, 2, 1, mark.
Here at the Vita Corporation Flight Simulation Lab in Warminster, Pennsylvania. Dr. James Winnery and other researchers are using a centrifuge to reproduce high-speed flight conditions. They hope to better understand the effects the G-forces have on the human brain.
That's it. You're going to have to really screen now, Rob. He's really going to maneuver.
This video of Winnery, recorded in 1985, dramatically illustrates what happens when pilots experience a blackout episode.
The first thing that happens is blood flow begins to be reduced to the head. So you begin to develop a tunnel vision. The next thing that we see is loss of motor control, loss of sensory input, complete loss of consciousness.
Okay, so let's turn this into a problem. So we got the pilots being tested inside a human centrifuge. So it's going to take 1 minute to turn through 20 complete revolutions. So 20 revolutions per minute. That's what we got before reaching its final speed. So this thing is going to be accelerated. It's going to take 20 revolutions per minute to reach its final speed. So what was its angular acceleration? So we have to assume that is constant. And what was its final angular speed in terms of revolutions per minute? So what is the final speed in terms of revolutions per minute? All right, so it's going to take 20 revolutions within a single minute to reach its final speed. So the first thing is, what's the acceleration, angular acceleration? And what's the final angular speed in terms of radians per second? So expressed in terms of revolutions per minute. Revolutions per minute. So that's what we're going for. So revolutions, this needs to be expressed in terms of radians. So 2 pi radians. So we got the answer in terms of radians. Okay, guys, don't forget when you do a pi, it's going to be 3.14 in your calculations. All right, so given all these symbols, including the top one, it makes sense to use the first equation. And from that, we can isolate alpha. Initial velocity is going to be 0, so that drops out. So this is going to give us the angular acceleration. And then plug the numbers in. All right, so we got the angular acceleration. Okay, now that we know the angular acceleration, so let's figure out the final velocity. We know the time, so for the final velocity. All right, so it makes sense to use this one because we got the time. We could also use the last one, but let's use this one. It's easier to use that one. Once again, the initial velocity is going to be 0, so that term drops out. We know what the angular acceleration is, which is this. We got the acceleration, so it's going to be 1 minute, so it's our 60 seconds. We got everything in terms of radians per second. Now do a conversion to revolutions per minute. Okay, once again, pi 3.14. Don't forget that. So the final velocity is going to be 40 revolutions per minute. Dynamics. Okay, so force acting on this mass is going to cause a torque. Torque is a rotational force. Okay, so force acting on this mass, and because it is pivoted to with respect to this point, with respect to the pivot, this thing is just going to experience a rotational force. This rotational force is known as torque. You take the force, multiply with respect to radial distance to the point of rotation. So it's going to give you torque. Torque is your rotational force. So the question is, what if this force is coming at an angle? If the force is coming at an angle, what you have to do is you have to find the component of the force, which is going to be tangent to this line, the radial line. Okay, so this is the parallel component. This is the component which is going to be tangent. It's going to be 90 degrees to this line that we're looking at. Okay, so it's going to be tangent to the arc that it's going to generate. That's what it means. All right, so notice that you end up, okay, let's just back out of it a little bit so you can see it better. All right, so this force is going to be tangent to the arc that it's going to generate. All right, so when you make a small triangle, so this is hypotenuse that you're looking at. This is going to be the base. So the force which is parallel to the radial or radius or the radial direction. That's the reason why you got two lines. It means parallel, and this one is going to be tangent to the arc that you're looking at. All right, so when you make a small triangle, this tangential component of the force is going to be the sine of the angle that you're looking at. Sine of the angle of this force that you're looking at. So you're always interested in tangential component of the force, which is going to be tangent to the arc that it's going to trace, in essence. So it gives you the sine of the angle. Sine of 90 is going to be 1, so it gives you this formula at the end. So this is the tangential force. Tangential force is going to be responsible for the tangential acceleration. So you could do a back substitution right there. And tangential acceleration is related to the angular acceleration. If you know the angular acceleration multiplied by the radial distance, it's going to give you the tangential acceleration. Okay, so let's do a back substitution into that formula to get a different expression for torque. All right, so this gets substituted into that, so it's going to give us that term. Okay, so it's going to give me an r squared, mr squared. And then stop at this point, and then let's do a comparison. So this is your torque is your rotational force, in essence. And this is your linear force. Okay, here's your acceleration term. This is your rotational acceleration. This is your mass. Anything in front of the rotational acceleration is going to be your rotational mass. Okay, so mr squared becomes our rotational mass. Okay, so instead of calling it rotational mass, we call this the moment of inertia. It means the same thing. So this mr squared is our moment of inertia, or rotational mass. All right, so in essence, you got mass, and then multiplied by the distance to the point of rotation squared. So the radial distance to the point of rotation squared is going to be our rotational mass. Now, this moment of inertia is a really powerful concept. Okay, so as you're about to discover. Okay, so here's your linear force. Here's your rotational force. This is your torque. A is your linear acceleration. Alpha is your angular acceleration. You got your mass and you got your rotational mass. Okay, so that's how you do a transformation. Rotational mass is going to be expressed in terms of the linear mass. You take the regular mass and multiply it by the square of the radial distance. Okay, so this is a Greek letter tau. So it's going to be our torque. It's going to be our moment of inertia. Alpha is going to be angular acceleration. Angular acceleration is in terms of radians per second square. Moment of inertia is going to be, this is kilograms, so this is going to be meters squared. And torque is going to be in terms of Newton meters. All right. Okay, so I'm going to map all the torque formulas, then express them in a single line. All right, so the torque is the tangential force, or tangential component of the force, which is the tangential component in the direction of the arc, times the radial distance to the point of rotation. That could be expressed in terms of mr squared, so this is your rotational mass, times the rotational acceleration. So I represent the moment of inertia, or the rotational mass.